All right. Good afternoon, everyone. We are Group 14. My name is Tyron Williams.
My name is Christopher Price.
My name is Timothy Oma-Taiga.
Today, we will be presenting our environmental engineering design project for an 11.21 million gallon per day municipal water treatment plant designed for the city of Watertown. This project is part of our environmental engineering design course, and our goal was to create a fully functional water treatment system that meets real world regulatory, operational, and engineering design standards. Our design is based on actual water quality data, EPA regulatory standards, professional design criteria, engineering calculations for every unit process. What makes this project challenging is that although the source is groundwater, it contains extremely high hardness, moderate turbidity, and microbial contamination. That combination means we couldn't really rely on a simple design. We had to develop a plant that combines physical, chemical, and biological removal mechanisms into one integrated system. Over this presentation, we'll walk you through raw water conditions, flow determination, treatment selection, unit process design, cost and sludge analysis, final effluent quality and system performance. And by the end, you'll see how our design acts as a real world municipal facility that can actually be constructed and operated. Okay.
All right. Next, we have our project overview. This project tasked us with designing a fully functional and operational municipal treatment plant that serves as a growing population while meeting both federal and state standards. Our design must treat at least 11.21 mgd, meet EPA drinking water standards, achieve Giardia disinfection requirements, eliminate hardness, and then produce water safe for human consumption. The city of Waterbury depends on this system for residential supply, industrial operations, fire protection, long-term population growth. And then the main challenges involved were managing extreme hard water, which is 315 mg over L, handling biological contamination, sizing all treatment units for peak flow, maintaining system redundancy. And then rather than designing one single solution, we treated this project like a real consulting firm would, and we optimized treatment performance, cost control, chemical availability, and operational simplicity.
And we have our raw water characteristics. Let's look now at the raw water quality and why it presents engineering challenges. The groundwater source contains a hardness of 315 mg over L and a turbidity of 7 NTU. The Giardia is also 2.5 cis per 100 milliliter, and the coliforms are 5 mpm per 100 milliliter. The raw water temperature is 14 degrees Celsius, and the pH was about 7.1. From a design perspective, hardness this high causes scaling, appliance damage, and customer complaints. Turbidity interferes with disinfection. The Giardia presents a serious health risk, and coliforms indicate biological contamination. This means the plant must soften water chemically, remove particles physically, and activate microbes biologically. We also evaluated the water as groundwater dominated by carbonate hardness, which is why lime softening becomes the best process option instead of ion exchange.
Okay. So, design flow determination. We calculated design flow using a practical planning approach. So, for our residential demand, we did 90,000 residents times 100 gallons per day, and we got 9.0 mgd. For the industrial demand, which would include furniture plant, steel companies, chicken processing plant, that total would equal out to 0.343 mgd, and the base demand would equal 9.343 mgd if you were to add them up together. So next, we account for fire protection, peak day usage, future expansion, and then we also added 20%. So that 11.21 mgd becomes our final design flow rate. And this value controls basin volumes, filter size, power requirements, chemical feed rates, sludge production, and every calculation in the report is based on that flow.
Next, we have our treatment train overview. This slide shows our full treatment train. We used a multi-barrier approach, which included a raw water intake, aeration, which was optional, lime softening, rapid mix, flocculation, sedimentation, filtration, UV disinfection, and then chlorine and storage. Each unit process has a specific process. Like lime softening removes hardness, filtration removes particles, UV kills giardia, and then chlorine protects distribution pipes. And then together, they form an engineered system that provides reliability, redundancy, compliance, and safety.
Here we look at our part of our design, which is lime softening. This is considered the heart of our plant. We can assume 80% is chemical hardness and 20% magnesium hardness. Using stoichiometry, our total lime dose would be 264 milligrams per liter, which would be a daily lime usage of 24,650 pounds per day. And by adding lime, we precipitate calcium as CaCO3 and remove magnesium as MgOH2. And we can finally reduce the hardness below 120 milligrams per liter. The trade-off, though, includes large sludge volume, a higher chemical cost, and potential with handling safety. But the benefits is long-term reliability and customer satisfaction.
All right. So rapid mix and flocculation. So in rapid mix, we'll see some high energy input. We'll also see that lime is instantly dispersed. So flocculation uses tapered mixing. So with stage one, we'll have high turbulence. Stage two, moderate turbulence. And then stage three, will be gentle mixing. And this allows microflakes to grow, settling to improve, filters to operate cleaner, and the total detention time would be around 20 minutes, and the total basin volume would be over 20,000 cubic feet.
All right. Next slide we have is sedimentation basin. Our basin is designed using overflow rate. Our SOR was 700 GPD per foot squared, and then our area was 16,014 feet squared, and then our volume was 1.4 million gallons. We selected 3-hour detention for reliability. This allowed to settle before filtration and prevented filter clogging, breakthrough events, and high turbidity spikes.
Okay, and then the next part of our design was our filtration system. We use 6 dual media filters, and the question was why dual media? This saves head loss, improves depth filtration, reduces backwash frequency. As far as each filter, they were 18 by 18 feet for a total of 324 square feet. Each Those six filters in total were 1,944 feet squared. The loading rate was 4 GPM per foot squared, and this ensures long running and stability.
All right, so UV and chlorine disinfection. So the UV provides primary disinfection. It also is a four-log Giardia inactivation. Chlorine provides residual protection and then distribution system safety. So the CT required equals 30 milligrams a minute. The residual equals 1.5 milligrams, and the time is usually around 20 minutes. Together, they act as a double barrier, a secondary protection, and also regulatory compliance.
Next, we have our final effluent quality. Our finished water meets turbidity under 0.3 NCU, hardness under 120 milligrams over liters, and then zero biological risk, and then chlorine residual intact. And this is like quality drinking water. Also, we have 4-log Giardia plus the virus inactivation.
And here we have our operating costs. Obviously, these costs include the chemicals, the electricity, and the UV energy. And the monthly cost we calculated was $22,000 to $28,000 per month. And this would definitely be considered competitive for a plant of this size.
All right, so sludge and residuals management. So 13.6 tons per day will more than likely be produced. Handling includes settling, thickening, and the disposal of these landfills. This protects the plant, the environment, as well as the operators.
We had a process flow diagram here, but for some reason won't let us see it. But this diagram basically summarizes the multiple treatment barriers, the control points, and then the system redundancy. Our full multi-barrier treatment overview, and these were like the key parameters and unit roles. Oh,
Yep, there it goes.
Okay, so in conclusion, our system meets EPA standards. It provides safe water, saves the city or the municipality money, and protects our future generations. As a group, we designed a real facility and not just a classroom example.
All right, that's it.
thank you.
Thank you.